Welcome to Summarize Science, where we break down fascinating new research. Today, we're looking at a paper that proposes a clever way to hunt for one of the biggest mysteries in the universe, dark matter. Imagine a massive galaxy sitting between us and a distant event, like two black holes colliding. According to Einstein, that galaxy's gravity will bend spacetime around it, acting like a giant cosmic magnifying glass. This effect, called gravitational lensing, can create multiple images of the same event, arriving at our detectors at slightly different times. Now, we know that galaxies are surrounded by huge, invisible halos of dark matter. Current theories predict that these large halos aren't smooth, but are filled with smaller, denser clumps or subhalos. The problem is, these subhalos are completely invisible, so how could we ever prove they're there? This is where gravitational waves, or ripples in space-time, come in. This paper explores how those invisible dark matter clumps would leave a distinct fingerprint on any gravitational waves that pass through them. For a galaxy with a smooth dark matter halo, there are strict rules about the lensed images we see. For example, if two images arrive very close in time, there's a limit to how different their brightness or magnification can be. This chart shows that for a smooth halo, the relative magnification between the two brightest images can't be more than 2. But the researchers' simulations showed that when you add in clumpy dark matter subhalos, this rule is completely broken. Suddenly, you can get image pairs that are far brighter relative to each other, a smoking gun signal that something is disturbing the lens. Finding a signal like this would be a clear sign that the gravitational wave passed through a lumpy dark matter halo. Another key finding is that these subhalos can create more bright images than we'd normally expect. Instead of the usual 2 or 3, we might see 4 or even more highly magnified signals from the same event, all arriving in quick succession. This complex lensing effect is what creates these beautifully intricate patterns, showing how much the subhalos can warp the image of a distant source. The researchers found that these special events could occur for about 1 to 10% of strongly lensed gravitational waves, making them potentially detectable. What's more, the chances of seeing these effects are highly sensitive to how dense and concentrated the subhalos are. This means that by finding these signals, we can start to measure the properties of dark matter itself. So, to recap the most important takeaways from this amazing research. First, invisible dark matter subhalos can cause unique and rule-breaking signals in lensed gravitational waves, like image pairs with unexpectedly high relative brightness. Second, they can also generate extra magnified images, giving us more copies of the same cosmic event. With upcoming and future gravitational wave detectors, we're expecting to find many more lensed events. By looking for these specific signatures, astronomers could finally get direct evidence of dark matter's clumpy structure. This would be a huge step in solving the dark matter mystery and would allow us to map the invisible scaffolding of our universe. Thanks for watching Summarize Science.